recording and we will get going. Okay, hey everyone, welcome to lecture today. So let me get my screen share going and we'll get started. We have a couple announcements for you today as we get started. Let me make sure I share the right window here. All right, and we are recording, perfect. Okay, and I have a better internet connection today, so I'm gonna try video and audio and we'll see how it goes. And if it doesn't work out, then I will turn off my video. Just let me know. Okay, so we just finished a quiz review off camera or not recorded. Now, I want to spend just a minute talking about the industry partner program. So everyone should be in a group at this point, and I'm going to go to our group project page. So UNCCV / well, actually, I'll just go here. So it has all of our repos. So the project, where is our project? Did I scroll past it? Course project, there we go. Cool, let me zoom in. Okay, so just one thing, please familiarize yourself with this README. So this README, it's a little long, but this has a lot of the information you're gonna need. So a lot of the answers to your questions should be here. So this is the README describing the course project. Now, the other thing that we're getting some questions about, so I think we have 6 industry partners right now. So around half the groups are gonna be working with a partner. And we had a few questions about the industry partner program, and we didn't have a chance to cover this in too much detail at the beginning of the course. So I just wanted to spend a few minutes for those groups who are working with a partner. I just wanted to spend a few minutes discussing, what the partnership program is, why we do it, and what to kind of expect, and kind of make sure that you have the right expectations in working with your partners. So this is kind of the one-pager summary, and to get to here, all you have to do is go to our course project GitHub repo, which again is in that UNCCV team on GitHub. It's publicly available, so no login required or anything like that. If I go to the industry partnership directory, this is basically exactly what we share with partners. So with our industry partners, these are local companies, local individuals around Charlotte. And the big reason we do this, it kind of goes back to when I was in graduate school. So I was in graduate school, I guess in 2010, so a decade ago, pretty crazy. But when I had the opportunity to teach this class, I thought back to, hey, what were the classes when I was in school that were really impactful, that I really remember and learned a lot from? And what were the classes that I kind of forgot about? And unfortunately, I forgot about a lot of them. A lot of the classes you take or that I took just, they were cool, but I don't remember anything. I took classes on circuits and all kinds of stuff. Anyway, so when I thought back, I remembered one class I took in graduate school, and it was actually a business class. So it was a combination of MBA students, business students, and engineers like me. And we did a project based, like the biggest part of the course was a project. And we entered this, it was actually a robotics competition, and we submitted this whole robotics thing to Bosch and actually won this competition. It was really cool. And doing a project like that where we had an external company that we were talking to really helped me kind of learn about industry. It was just a really cool way to get experience kind of in practice, because I can talk your ear off about computer vision all day, but I think until you see some real applications or some real research that's being done with computer vision, I don't know if it's really going to fully sink in, because it might just seem like theory, right? So the whole point of this is to get you in contact with local people who are doing things in computer vision, so you can work together on a real project. Now, these are still pretty small scale. It's not like you're an intern or you have a job at this company, nothing like that. Really, the partner is there to give you some direction and some guidance. Partner teams are required to meet with our students 3 times over the course of the semester. And a lot of partners will have pretty specific directions they want you to go. They'll say, oh, please work on this problem. This is relevant to our business. And that's the idea, is they provide direction in a project. They may provide some data. And really the thing to be careful that I want you to be aware of, this is not like a contract work for hire thing. So it's not like we're like, saying, oh, these students are going to work for free for you. That's not really what we're trying to do. We're trying to get you guys to partner on something that's interesting to these businesses or these people that you partner with, so they can tell you more about the world that they come from, the problems that they solve. So it gives you guys some direction, some context, some information. And then for them, they can learn more about computer vision. And the real hope is that it makes some connections. And you guys, a great outcome from this is that maybe they would like to hire one or more of you guys as interns, or maybe you learn more about that industry and you can figure out if it's something you want to do. That's really the point. It's not just about delivering a project. The projects are important, of course, but that's really the idea, is to create more connection in the Charlotte community. So that's the relationship with partners. If you are working with a partner group, I hope you enjoy it. I think a lot of students have in the past. Just do your best to communicate well with them, listen to what they're interested in, share your ideas. You'll have meetings with the TAs and myself too to help guide you. But that's the idea with the Industry Partner Program. Before we move on, are there any questions about the Industry Partner Program? If there are, please throw them in the chat window. Okay, all right, hopefully that'll make sense. Okay, one more question, meeting and such. I need more details, Hernan, more details. You mean like, when are you meeting? While Hernan is thinking, let me go ahead and hop to our next announcement, and Hernan, I'll come back to you once you, if you can provide more detail on your question. So let's see here, industry partner overview, intro to programming challenge. Yes, so let me hop into the programming challenge real quick. So just to review the schedule here. So the next thing that you have due, let me make this a little bigger. Cool. So you have project stage 2 due at midnight on 10/19, which is, what is today? It's in about a week. No problem, Hernan. Oh, so Hernan's asking, how do you count the number of meetings? Oh, you mean the meetings with the partners? So the TAs will be on some of those meetings. If not, we'll just, we trust you that you had that meeting, and the partners talk to us too, so we'll hear. But yeah, the partner's responsibility is to have 3 meetings with you guys to make sure they give you enough information and guidance. Yeah, we'll either take your word for it or we will talk to the partners. So we just talk to everybody pretty much. Okay, cool. So the thing I want to get into is I want to introduce you to your programming challenge. This is a really cool programming challenge, I think, but it's hard. It's much harder than the last one, so do start early. And you don't have all the information yet, but you're about to start getting into it, and it is time to start on it soon. So as we mentioned last time, there's only one programming challenge for these 2 modules. So we have put these 2 modules together into one module, basically, as far as the programming challenge. So this programming challenge is for modules 3 and for 4. And for this programming challenge, I think this is really cool. You get to train a neural network to drive a car. That is the idea. So let me show you the page. So the next module that we'll do, so again, I'm just here in the UNCCV team. If I go down to autonomous driving, that's our next module. There it is. And I click here. So here's our next module that we'll get into in about a week or so. If I go to challenge, here is a description of the challenge, and please do go read this soon. So we're going to cover all this in a bunch of detail in the autonomous driving lectures, but it's not too early to get started now. So we're going to talk more about neural networks today and about perceptrons and Frank Rosenblatt and all that cool stuff. But what you're going to be doing in this module is you're going to be training a neural network that you create. And you'll use some of my starter code basically, but you'll have to do some changes to it. You're going to be training it to take in images. This is images of a road, right? And predict what angle to turn the steering wheel at to drive the car. So that's what you'll be doing in this programming challenge. This data was taken from my old job. I used to work at a company called Autonomous Fusion in Atlanta. And this is our test track. It's right in front of Turner Field. It's pretty cool. And I was able to convince my boss to let us share this data. So you have some driving data to use. And you'll be using this driving data to train a neural network to drive or to steer, not to do the gas and brake, but to do the steering wheel to steer a car. And Hernan asks if this is like reinforcement learning. So yeah, great question, Hernan. This is not reinforcement learning. RL is really cool. If you're interested in RL, there's some good groups on campus you can join. There's one of my coworkers is really into RL. I can make some recommendations for you. So RL stands for reinforcement learning. And you can use RL for autonomous driving, but it's not quite there yet. So the most of the cutting edge machine learning approaches in autonomous driving do not use reinforcement learning. It's not quite production ready yet. So you're going to be using supervised learning, not reinforcement learning. Good question. We don't do too much RL in this class. It's just for a couple of reasons. We don't quite have time for it, but it's a very interesting area. So this is going to be your challenge, and please, as soon as you have a little bandwidth, come look at the instructions here, look at how we're going to evaluate you, and start thinking about this programming challenge. The methods you'll be using and stuff will become more clear, especially as we get into this lecture. But this is going to be your challenge. It's going to be training a neural network to steer a car. So do have a look at that soon. Okay, and then I think do we have one more announcement, or was that it? Let's see. Oh, that was it. Cool. So we did the programming challenge. Great. So let's get into our lecture. Before we do, Arvind and Rohan, did I miss anything? Any announcements from your side before I hop into lecture?
Nothing, Professor. That's what we discussed.
Perfect. Thank you so much. All right. Just wanted to make sure I didn't miss anything. Okay, guys. So we have about an hour. So let's dig into it. So we have a fun lecture today. I like this lecture. I think it's pretty interesting. Hopefully you guys do too. So just as a reminder, last time we started off with some fun questions, thinking about consciousness, how brains work, stuff like that. We talked about these guys, McCulloch and Pitts. They developed a mathematical model of a neuron. We discussed that. We walked through how the math works. We talked about how the model works. We decided that in the two-dimensional case, a McCulloch and Pitts neuron can divide the plane into two areas divided by a line. So that's great. And then we talked about Frank Rosenblatt. He took McCulloch and Pitts neuron and figured out a way to train it using a very simple algorithm. His perceptron algorithm, he called it. It works just like this. It's very simple. So we have, let me zoom in one more time. It's very simple. So it takes in some weights, it takes in some input, and it takes in the current label basically from your data. And we go through our examples one at a time. If we get an example wrong, we either add or subtract our example from our weights to adjust our weights. And if we get our example right, then we don't do anything. So it's a very simple learning algorithm invented by Frank Rosenblatt back in the 1950s. And what's really cool, and what hopefully I showed you last time, is that this algorithm is capable of, given enough steps, it can always find the answer. So always, if there is a linear separator that divides your examples into two areas, this model will always find it, which is pretty crazy, pretty unique. I think that's pretty cool. So Frank Rosenblatt was very excited about this. And he didn't just do this in two-dimensional space, right? He did it with images, right? And the images he used, as we discussed last time, his images were 20 by 20 pixels, right? So really, he's doing this problem in 400 dimensional space because there's 400 numbers that describe each image, 400 pixels in each image. Okay, hopefully that makes sense. So what I asked you last time is I had you think a little bit, and I said, okay, do you think that if we use Frank Rosenblatt's algorithm, can it separate, for example, these 9 images of balls from these 9 images of bricks? And these are just synthetic, simple images. And I think around 70% of you said yes, and you got it right. So it is able to do this. And just one little point I'd like to make. The analogy here, and it's not even an analogy, it's reality. So just like the perceptron algorithm can learn a linear classifier, a linear line to tell apart or separate these points, the yellow from the blue points, the image example is exactly the same. So instead of having points in two-dimensional space that are described by an x1 and an x2 value, our images are just points, but they're in a much higher dimensional space. They're in a space that's equal to the number of numbers you need to describe the image. And in this case, it's a 20 by 20 pixel image. So that's 400 numbers. So images, in this case, are just points in 400 dimensional space. So when we run the perceptron algorithm on those images, we're trying to find a shape in that high dimensional space that separates the brick images from the ball images. So it's exactly like this, right? It's just higher dimensions, right? I know I'm probably glossing it over it a little bit, but that really, it's the same exact math, just higher dimensional space. Math is identical. Just one other thing, so in that higher dimensional space, we aren't finding a line anymore. What kind of shape do we actually find? Throw it in the chat window if you know. What do we call this shape and it's actually a 399 dimensional shape that we find to separate our examples. Yes, thank you, Jagadesh and Abhijit. Yep, it's a hyperplane. Perfect. So we're trying to find that hyperplane. Okay, so we saw last time that we were able to find a hyperplane to separate the synthetic data. And we got to the really fun question. This is kind of the end of this first lecture, and then we'll hop to the next lecture. So this, I think, is the really fun question, right? Can we do it, right? Can we tell apart real images of bricks from real images of balls using Frank Rosenblatt's perceptron algorithm? And we started here and we said, okay, here's the visual we're going to use. We're going to go through our data one at a time, right? And for each point, we're going to decide if it's correctly classifying our image. If it is, I'll draw a green box around it. If it's wrong, I'll draw a red box around it. And here we got our image correct. And the last thing I said is, hey, I'm going to visualize my weights using an image, basically. And let me ask again real quick. So remember that the dimension of x, so x is a vector that's 400 long. It has one value for each pixel in our images. What is the dimension of w? I asked last time. Let me ask again just to make sure we got it. What is the length of the vector w in this case? Thank you, Abhijit. It's 400. Perfect. All right, and I'm going to visualize the vector as an image, actually, because what really happens is when you do that dot product, imagine taking this image, moving it over here right on top of these weights. Every pixel on the image is multiplied by a corresponding pixel in the weights. Um, and yeah, and every image is multiplied by a corresponding pixel in the weights. And that is how we compute our dot product. Cool, and I see real quick, so Arvin, do you want to make an announcement after? Don't let me forget. So Arvin, if you can just remind me at like 3:40, and we will switch to your Calendly announcement. Does that work?
Sure, Professor. Sure.
Perfect, great. All right, awesome. Thank you. All right, great. So that's the idea here, guys. So that was step 0. Here's step 1, and because, let me ask you guys real quick. So notice that the weights didn't change, right? These weights, this is step 0 here, step 0. And the weights are just all zeros. It's just a flat, blue image. After step 1, the weights are still all zeros. Why did the weights stay 0 after one step of the perceptron algorithm? So if you know, throw it in the chat window. Why did they stay 0? Yeah, Jagadish got it right. We classified the image correctly, right? So this is correct. Our algorithm said ball, our little neuron said ball, and it is a ball, so that's great. Okay, so step 2, again, we got it right, so nothing happens to our weights. Now here's where it gets really interesting, right? Here's step 3. And what happened to our weights, right? So we got it wrong. So when you get it wrong, remember you either add or subtract your example from your weights, and store that as your new weights. And here, depending on which way you get it wrong, here we got it wrong. So we actually add this brick image to our weights. And this is the new output. So that's pretty cool, right? Okay, so really you can visualize the weights you've learned as an image, and that's going to be really important in neural networks. Okay, so let's do another step. Here we go. Okay, so look carefully at this image. What do you see happening? Please describe in words in the chat window if you know. What has happened to our weights on step 4? What do you see happening? Yeah, exactly. So someone said ball plus brick, and you're very close. It's actually not ball plus brick, though. A bunch of people said ball plus brick. You're close, but it's actually, importantly, it's not ball plus brick. What is it? Not ball plus. Not ball times, good guess. Ball minus, thank you, Abhijit, good. So remember, in Rosenblatt's algorithm, if the answer is supposed to be 1 and you say 0, you basically add the weights. Add the example. But if the answer is 0 and you say 1, you subtract them. So if you get it wrong the opposite way, you subtract instead of adding, basically. So here we added the brick, but here we subtract the ball. So that's really important. That'll come up more. But yeah, so right, so we've learned, what we've learned so far is that if you multiply the examples of balls times these weights, right, and add the result all together, you'll get, on average, a bigger number. And if you multiply an image of a brick times these weights and add it all together and do the dot product, you'll on average get a smaller number. That's what's basically happening. So we still have yet to see if after learning for a while, it's going to be able to correctly classify all 9, right? We'll see what happens. But this is as simple. This is it. This is the perceptron algorithm. I hope it makes sense to you. All you do is you go one example at a time. If you get it right, do nothing. If you get it wrong, either add or subtract your image from your weights. That's all there is to it. So let's keep going here. So now I'd like to visualize the first 10 steps together. And we're going to do more steps in a second. But here are the first 10 steps. So you can see we get to step 5. Here's 6, nothing happens. Get to step 7. Now we've actually added this ball, right? So these weights kind of get more and more complicated. But as they progress, as these weights progress, you still are just seeing, right, balls and bricks added or subtracted, right? That's all we're seeing. And I won't talk about this for too much time, but this is actually, so remember that when you do the dot product, the result is just one number, right? So when I take a given ball and multiply it by the weights, do the dot product, the dot product result is just one number. And here I'm plotting that one number. I'm plotting it, and I'm visualizing the color, whether it's a ball or a brick, basically. And if we finish this successfully, if we train correctly, basically all the blue dots will be on one side and all the yellow dots will be on the other. That means you've actually separated our space correctly in high dimensional space. So I'm about to scroll down, and I think we'll train for like maybe 1,000 steps, something like that, and it'll be the same animation. And we will see if Frank Rosenblatt's algorithm can tell the difference. So think for a second in your head, what do you think, right? Do you think that it will be successful? Will this very simple algorithm where you add or subtract the pixel values from the weights, will this be able to solve the problem? Okay, here we go. So here is the sped up animation. So we're doing a whole bunch of steps, you can see, right? And it turns out if you keep going for a while, it's already kind of gone long enough that all the blues separate from all the yellow, basically. I think it finishes learning right. When does it stop learning? Right. It's probably a little hard to see on the screen share. I would look at the lecture notes later. Hopefully the animation looks okay. But yeah, so around step 2 or 300, it's done. It has learned to perfectly separate these bricks from these examples of balls. Just by doing this add or subtract the weight trick, right? So these weights have learned enough about what bricks and balls look like to correctly separate them. Now, some of you might be suspicious, and you should be, because we just had a module about how you should be very suspicious of learners. So what should we check to make sure that we're not just like totally wrong here? What would be a good thing to check to make sure we haven't made a mistake? We could check accuracy, but yeah, definitely test data, right? Mm-hmm. Yep. And this part of the model is not really about that, but just to make sure, I did do a test when I ran this experiment. And we actually do achieve very good accuracy on a new test set. We achieve on average between 60 and 100% accuracy. The average is about 80%. So it is learning. So actually 85% is the average accuracy. Now there is some deeper math going on here, and if you are at all suspicious about the 400-dimensional space thing, or if you want to learn more about it, there's a really great book. I've recommended it before, and there's also a course that goes along with it called Learning from Data. There's this idea in machine learning called the VC dimension, and if you want to think more about that high-dimensional space and kind of learn more about the math of what kind of classifier can separate data in what dimensional space, then do check out this class from Caltech. It's called Learning from Data, and there's also a great book called Learning from Data. We don't have time here today, but just in case you want to learn some more, there is more rigorous math behind this, and it's the mathematics of the VC dimension. Okay, so now I want to just have a little bit of fun commentary. Yeah, so Hernan said, can it detect images with different dimensions? Yeah, so pretty much, so Hernan, when we get into deep learning, we are going to figure out how to make this work with bigger or smaller images. But Hernan's question basically is, okay, what if an image comes along and it's like 30 by 30 or 40 by 40, right? Or God forbid, what if it's like full HD, right? What are we going to do? So no, this only works, Hernan, with 20 by 20 because it was trained on 20 by 20. But in the deep learning module, we're going to learn about something called adaptive pooling. That will let us train on any size, basically. But we aren't there yet. So back in the 50s, Rosenblatt had to have 20 by 20 images. Great question. Okay, so this is really fun. So if you go back and look at the press, so look at what was being printed in the papers. So remember that the 1950s and 60s, that was the first wave of excitement about artificial intelligence, right? And there's been 2 since, so there's another wave in the 80s, and now we're in a wave of excitement about artificial intelligence. The first wave was maybe even sillier than today's wave. So here is an article in the New York Times, and these are articles written about the perceptron algorithm. So this research was taken in part with the Navy. The Navy funded part of the research, or maybe all the research, I'm not sure. But listen to this quote. This quote it's awesome. So this is in the New York Times, a very reputable newspaper. It says, the Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. So this is what the New York Times said about the algorithm that you just learned. So exactly the perceptron algorithm, okay? All right, let me give you another quote from the New Yorker. So talking about the perceptron, they say, which, as its name implies, is capable of what amounts to original thought. So the New Yorker said that this algorithm was capable of original thought. They also said that it can tell the difference between a cat and a dog. That wasn't quite true. And they also said that someday we may find, oh, this is, I'll just share one more quote for you really fast. So obviously people got really excited, right? They thought, holy crap, we've solved artificial intelligence. And just one other quote that I think is really interesting. So although people got really excited and kind of ahead of themselves, the same technology really has become deep learning today, and it can do some pretty remarkable stuff. But way back in the 50s, it wasn't clear at all like what you could do with deep learning. Like today, deep learning can do all kinds of stuff like diagnose diseases, like really cool stuff like that from medical images. But when Frank Rosenblatt, when he was asked, and I'm not making fun of Rosenblatt, it's just interesting because it's amazing how hard it is to predict the future is kind of what I'm getting at. Because there's this, listen to this is great. So the New Yorker interviewer, he said, what practical use, we asked, would the perceptron be? And Frank Rosenblatt, the inventor, said, at the moment, none whatsoever. Dr. Rosenblatt said cheerfully, someday we may find it useful to send one to outer space to take impressions for us. So that was the only application that they could think of in the 1950s. So I just think that's really cool because think of the technology we have today, right? And think about the applications that we're thinking about. If we're this far off, right, it just says that even the people who are the experts in the field don't really know what's going to happen, right? It's very hard to predict the future, which is exciting. We don't know what's going to happen, and there's lots of room for innovation. So I think these quotes are really, really interesting, and I think hopefully it gets you thinking about how people think about AI today. And hopefully in this class you learn some more about how AI really works, and you can make your own decisions about how we should be communicating it to the public. Okay, so I've got some fun questions to think about later if you'd like to, but let's go to the next chapter of our story here. So the next chapter is pretty much this. So you might remember Marvin Minsky from earlier in the course, and maybe Seymour Papert. So these guys are researchers at MIT. So in 1969, so perceptrons basically got really popular, AI got really popular. So in 1969, these guys published a book. They actually called it Perceptrons, which was kind of mean because in the book, they really bashed perceptrons. They showed all this stuff that perceptrons couldn't do. They really criticized perceptrons very heavily. And a number of people believe that this big criticism led to people, kind of giving up on neural networks, and no one really studied neural networks, at least not a lot, for the next 15 years, really until the 1980s. So this book came out. It was very critical of perceptrons. And there are cases where perceptrons fail. So here's three examples. Minsky and Papert used one of these in their book. But if you look at all these cases, right, here is Rosenblatt's perceptron algorithm trying to learn as best it can. And it can't, right? There's no linear separator. It's useless, right? So if we think about images of cats and dogs, for example, is there really going to be a linear separator? Maybe we'll find out in neural networks, maybe. When we get to deep learning, we'll see. But in these simple two-dimensional cases, the algorithm is fooled, right? So there are very simple examples where perceptron fails. And there's a bunch more criticism made in that book. If you're interested, you can buy this book for very cheap on Amazon. You can learn all about what Minsky and Papert had to say about perceptrons. So let's keep moving here. And I have a little more information in case you're curious. You can learn a little bit more about the history. But what I want to get to now is this. So for whatever reason, maybe it was the perceptron book, maybe other reasons, people didn't really work on neural networks for another 15 years. So not until the 1980s. In the 1980s, these two folks, so Jeff Hinton, who you'll hear about again, and David Rumelhart, they figured out how to do something pretty cool. So as I've shown you, the perceptron algorithm, it really only trained one neuron, right? So we just had one single neuron. It could have a bunch of inputs. It could have like 400 inputs, right? No problem. But it only trained one neuron, right? In the 1980s, Hinton and Rumelhart, these researchers, they published a paper in Nature, the journal Nature, and they showed how using an algorithm called backpropagation, they showed how they could train combinations of neurons that could be multiple layers deep. Excuse me. And what this did is this opened up a new world of possibility where now we could learn things that are more complicated than linear separators. So that linear separator, right, that was kind of a limitation. So thanks to this advancement in the 1980s, we could all of a sudden learn more complicated patterns using neural networks. So that's a big advancement. And we're about to get into some neural network math, and it's really going to be all about backpropagation. So backpropagation, this really is the algorithm that trains modern neural networks, and it was invented back in the 80s, and we're actually about to learn about it. Okay. So just one last thing I'll say about the history. So this is my very last kind of slide on the history of neural networks. Is that, so there was a lot of excitement in the 80s. That kind of went away in the 90s. People started researching things called support vector machines and other kinds of machine learning. But in the 2010s, starting about in 2012, neural networks came back and became very popular. And we're going to get into that in a lot of detail in our deep learning module. But the last thing to know is that the first paper that really kind of demonstrated really strong performance was again from Jeff Hinton, that same researcher from back in the 80s. So it's funny, at the beginning of his career, he published this important paper. He thought neural networks were awesome, right? And then for like 15 years, no one really cared, right? So no one was interested, he wasn't a terribly successful researcher. And then all of a sudden, in 2012, he published this paper with his graduate students and like blew everything out of the water. So it's kind of interesting how things come and go, right? So if you're feeling like whatever you're working on is underappreciated, that can always change. So things take time sometimes. Okay, so that's a brief history of neural networks. I might ask you a conceptual question on the quiz about this. Again, if you're looking for study for the quiz, please look at the questions that I ask you, all these multiple choice. This one probably not, but some of the multiple choice questions I asked you. What did I ask you at the beginning? I think, oh yeah, something like this. I could definitely ask you something like this on the quiz. I could ask you something like this. So do review those as you prepare for your quiz next Monday. Okay, so we have a little bit over half an hour, and I'll make sure we have a little time for the announcement at the end. Don't let me forget. But now I really want to get into neural networks. And we've been talking about the history of neural networks, but now it's time to talk about the mathematics, right, and the code, right? How do we build one of these, right? How do we actually make one of these things work? Okay. And just so you know, we talked about the perceptron algorithm, right? And we did that in Python. We're going to go a step further now, and we're going to do the backpropagation algorithm. And the reason we're doing that is because backpropagate. So the perceptron algorithm from Frank Rosenblatt, it can only train one neuron, basically, right? We want to train many neurons because we can learn more complicated functions using many neurons connected together. And the way you do that is with backpropagation, and that's what we're about to learn. So that's why we're doing this. And backpropagation is how deep neural networks are trained. Great. And then last thing I'll say, you do have some videos to watch for this. So this was the first YouTube series I ever made back in like 2014 or something. So do watch these. I think they really will help. This series is a little bit dated now. Here's an ad that we get to watch at the beginning. But yeah, I released this video 6 years ago. Back then, people, there were way less resources. Today, YouTube, there's so much good stuff. Back then, there was way less. And this video has done, has way more views than I ever would have expected. And really, this was just me explaining how neural networks worked. But this is what you'll be watching as part of this series. And this will explain the math and the code as well. It goes a little bit fast sometimes. Feel free to pause. And I would like you to look at the lecture notes. Those two things together should give you a good understanding. Because what I really want you to have by the end of this module is a good understanding of how the mathematics of backpropagation works. Okay, so all that said, let's get into some real examples. So what I'd like to do, I think the best way to learn neural networks is to do an example. So we are going to, in the rest of this module, we are going to train and code and figure out the mathematics of a very simple neural network, but it will be more than one neuron. more than one layer deep, it'll be 2 layers. And we're going to do it on some real data. We'll get some real data here because that's helpful. And the premise is just a toy example, but it'll help us think through it. So let's say that you're trying to prepare for your next test. We don't have tests in this course, so maybe it's for a different course. Let's say you're trying to get ready for your next test, and you're trying to decide how many hours you're going to sleep and how many hours you're going to study. And based on those two, you're trying to maximize your test score, right? You want to get the highest test score you can. And on your last 3 tests, you recorded how many hours you slept. So this night you only slept 3 hours, not great. And how many hours you studied. Here you studied 5 hours. And you recorded what your score on the test was. So the idea is, can we train a neural network to predict what your score on the test will be if you study for X hours and you sleep for Y hours? So that's the idea. Just toy data. It'd be fun to do with real data one day. It'd be interesting to see what you learned. Okay. If anyone has real data, share it. That'd be cool. We could see what the model learns. Okay. So here I'm putting the data into Python. Did I import this? I think I did. Okay, so I'm putting the data into Python. So here's X. So this is our hours sleeping. And this is our hours studying here. Here are our labels. These are what we're trying to predict. These are our test scores, 75, 82, and 93. Let me remind you, I don't know actually if this is reminding or if this is the first time I've told you. So this is a certain kind of machine learning problem. The name I would use to describe the problem we're about to solve is I would call this a supervised regression problem. Okay, so let's take a step back and make sure we know what those words mean. So throw it in the chat window if you know. What does supervised mean? Why is this a supervised machine learning problem? Yeah, we have labels, right? We have labeled data. So in unsupervised learning, which is a whole area, we'll cover GANs later in this course, and you'll get to see a little bit of unsupervised learning. But if we only had the hours sleep and study, that would be unsupervised. But because we have these labels, this is called a supervised problem. Okay. Now, what about regression? Why is this a regression problem? So yeah, Abhijit said it really well. It's a continuous Y. Yep, totally. And if we weren't doing a regression problem, what are some other options? What's another type of machine learning problem we could solve that would not be a regression problem? Classification. Good. Yep, perfect. So if we were trying to predict like, your test score of like A, B, or C or something like that, that would be a classification problem. Okay, cool. Oh, one more question for you. When you go to solve this problem, right, when you try to predict the steering wheel angle on your programming challenge, will that be regression or classification? Yeah, so most folks say regression. It's really interesting. You can actually solve this as a classification problem by breaking up all your angles into different bins, different categories. And you actually will get better performance that way. But at face value, it's a regression problem, totally. And there's also multi-class problems, Monica. We'll talk about those, I think, a little bit later. But for now, classification and regression are kind of the 2 big categories. Okay. So let's see here. The first thing is we need to scale our data. I can't tell you how many networks I've tried to train and I forgot to scale my data. So neural networks are smart, but not quite smart enough to know how to scale our data for us. So generally scaling your data between 0 and 1 is a smart idea. There's other ways to scale. You can divide by the standard deviation and subtract the mean. You can do things like that. But here we're just going to scale it between 0 and 1. So we'll scale our data. So here's my scaling. I don't think, yeah, well, yeah, maybe I'll talk about it just for a second. So here I'm dividing this test score by 100 because the max score is 100. And here I'm dividing x by the maximum value. Why am I doing an argmax though there? Is that a typo actually? That's interesting. So argmax gives me the index that has the maximum value. And I'm curious, why am I doing an argmax there? It seems like it should just be a max. If I do argmax, comes out the same. That's weird. So remember, argmax is going to give us the indices of the maximum value. And this is probably a little bit of a distraction from our main topic. Oh yeah, that's a typo. This should be max, I believe, unless I'm missing something. I guess those end up being the same. That's just a coincidence. So we're dividing by our max value. There we go. Okay, cool. All right. And actually, I ran this cell twice. Amax is not argmax. So is that right? Did I forget something? Let me see here. np.amax. Okay. Return the maximum of array. Oh yeah, you're right. Yeah, thank you. Interesting. So what's the difference between Amax and max then? It's the same thing. It's along a certain axis. Okay, thank you, Akshay. I forgot that. Okay, interesting. Cool. I guess I normally use max, and for some reason, so there's also a function called argmax, which is different. Okay, cool. All right, interesting. Okay, so we'll leave that alone for now. If you're curious, go check out the documentation. I'll put it back to Amax then for now. That's fine. Cool. Thank you. All right, and I noticed I made a mistake. I ran this multiple times, which has compressed our data too far. So let me go back here, run this again, and I'm just going to run this once. Okay, we've scaled our data. So let's get into our terminology. So this diagram, this shows the architecture of the neural network that we're going to build in this series. So these circles are called input units, and they just kind of hold our input values. So one of these units is going to hold our number of hours of sleep, and the other one is going to hold our number of hours of study. If we had a third variable, like, I don't know, how much pizza you ate the day before or something silly, that would be a third input unit. So generally, each of these input units is connected to our neurons. So these neurons here, these 3 circles, and actually this circle as well. So these 4 circles, each of these is exactly what we learned last lecture. These are exactly McCulloch and Pitts neurons. Let me go back there just for 1 second. So remember, we started last lecture by learning about McCulloch and Pitts. Here we go. And I think it's interesting that, hey, you know, these guys set out to try to figure out how your brain works, and this is supposed to model your brain, and it does to an extent, but certainly not anywhere near perfectly. But today in deep learning, we use the same exact formula. So this model of the neuron, this neuron model is exactly what we're doing in these equations. Actually, no, I take that back. Sorry, it's not exactly. There's one little extra thing. We have what's called an activation function. We'll get into that into detail, but it's very similar. So there are 4 neurons in our neural network. Now, why we laid them out in this orientation, there's just a couple things to know. So we have to have one output neuron because we have one output number. But there's no reason you couldn't predict 2 things. You could predict your score on a test and your score on a quiz or something. I don't know. You could predict something else. You could have 2 outputs or 3. And that would just mean you have more output neurons. But because we're predicting one variable, your score on a test, then we have one output neuron. Now this layer, so it's organized in layers. This is called the hidden layer in the center here. And here we could have any number of neurons. I've chosen 3 to kind of make things simple, but it could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It could be whatever. And that's something that you may tweak or you may change as a computer vision practitioner. You may change this. You may experiment with it, but it's not going to be learned. So the network will not learn how many neurons it should have. You have to decide, basically. Okay, and these connections are called synapses. All right, so the connections have a really simple job. So we take our input value, and each of these lines, each connection, each synapse, it corresponds to one weight. So remember those weights that we learned about last time, that W vector, right? Every line in our diagram here corresponds to one weight value. And the weights are just multiplied by their inputs. So if I have a 3 input value and a weight of 2, those multiply together to pass a value of 6 into the neuron. So that's all there is to that. Now neurons, so these do exactly what we discussed. And actually I could probably, I don't have my weights here. Yeah, I guess this is supposed to represent after they've been multiplied by the weights. Yeah, so after you multiply the value that comes in by the weight, you add all those values together. That's the dot product we saw last time. And there's one more special new thing that we're going to do. And this is something that McCulloch and Pitts didn't do. And it's for a good reason. It lets us learn what's called a nonlinear function. And the thing we're going to do is we're going to pass that new value, this new value that we compute, the output of the dot product. We're going to pass it through what's called an activation function. So the activation function is going to kind of smooth out these values. So let me show you. So the activation function we're using here is called a sigmoid activation function. And there are many functions out there. That's right side, sigmoid, good. There are many functions out there. In deep learning, one that's become very popular is called a ReLU. Back in the 80s, the sigmoid was pretty popular. But yeah, Rohan, ReLU is perhaps the most important or most popular, ReLU or leaky ReLU. We'll get into those in the deep learning module. But for now, we're going to use sigmoid activation functions. And this brings us to our first poll of the day. So let's get the poll ready, if you don't mind, please, Arvind of Rohan. Thank you. And what I want you to do is, here's the function that I'm giving you. I'm saying, hey, this is the function that we're going to pass the output of our neuron through. And it's going to help us learn basically more complicated patterns. And yeah, please take about 45 seconds and see what you think. So which plot correctly shows this function? So I'll go ahead and stop talking now. And yeah, take 45 seconds and we'll talk about the answer. Okay, thank you. Was that Arvin or Rohan? Who should I thank?
Good.
I'm handling it, Professor.
Thank you, Rohan. Okay, great, awesome. All right, cool. So the most popular answer is C. The second most popular is B. All right, let's hop into it. So what I would recommend here is I'd recommend just plugging in some test numbers. So if I plug in a very large number for Z, let's say like 100 or something, right? What is e to the minus 100th power? It's going to be very, very close to 0. So 1 plus 0 is 0, or 1, excuse me, and 1 over 1 is 1. So as our numbers get very, very big, this function will approach 1. So it should be, for that reason, either B or C. B or C should, actually be C or D, excuse me. The next thing we're looking for is what happens when Z gets really small. So as I have very negative values, so like let's say that Z is like negative 100. If Z is negative 100, then e to the minus 100 is e to the 100th. E to the 100th powers is huge. And 1 over a huge number is basically 0. So for that reason, it's not D. It won't approach negative 1. It must be B or C. So the last thing to do is just figure out, kind of what the value would be at a more reasonable number. And I would just plug something in, is what I would do. So I'd recommend plugging in perhaps 1. So if you did 1 over 1 plus e to the minus 1, e to the minus 1, you can plug that into your calculator. It's like 0.6 or something like that, I think. And you can plug that in and see what you get. I believe the answer ends up being C. It should be C. Well, let's do it, I guess, for fun. So I'm just going to use my favorite calculator, Google. So let's do 1 divided by 1 plus e to the minus 1. If I plug in 1, what do I get? I get a value of 0.73. Great, and I get some videos about the integral of the sigmoid function. Cool. All right, so let me go back here. So yeah, 0.73 with a value of 1. So 1 is about here. So that looks about right, like 0.73. Here, if I have a value of 1, actually, now I'm really wishing I had plugged in 2.5. That'd be a little better. But here, I think the value is a little bit too high. So I believe the answer is C for that reason. So if you got C, great job. Okay, so that is what a sigmoid function looks like. Now let's really get into our network. So there's going to be some calculus. This is probably the most mathematically intensive unit in the course, so hang in there. So these are the mathematical equations that explain how to take a given input into our neural network and how to pass it all the way through to make a certain output. So F is our activation function that I just showed you. It's that sigmoid activation function. And this is maybe a little bit different than the math you would have seen in high school, for example, because the variables here, they're not, they aren't scalars. So these are all matrices. So this is matrix math. So this very much relies on linear algebra. So hopefully most of you at this point have had a linear algebra course. If you haven't, it's not too bad, I promise. I think it is a requirement though, so most of you should have had a linear algebra course. And let's get into the math of how this works. And I've given you a nice little table here to kind of give you an idea of all the key variables that we need to keep track of. So X is our input data, for example. Y is our output data. Our weights, those are stored in 2 different matrices. Let me scroll up real quick just to get you kind of thinking here first. So remember that Frank Rosenblatt's perceptron algorithm, he processed 20 by 20 grids, 400 pixel images. How many weight values did his perceptron have? Throw it in the chat window. How many weights did he have? How many numbers? 400, yeah, might be 401, 400, yeah, something like that. Perfect. Okay. How many weights does this neural network have? How many weights? How many numbers do we learn? How many weights are there? Yeah, so I see a 9. I also see a 2 and a 6. Yep, so 9 is the right answer. Right, good. So those of you who said 9, how did you know it was 9? How did you get the answer right? Why is it 9? It's the number of connections, right? Yep, exactly. So every line corresponds to 1 weight, right? Perfect. So there are 9 of them. And we're going to store these 9 weights in 2 different matrices. So we're going to store it in a weight matrix called W1 and a weight matrix called W2. And basically every layer in a neural network, so by the end of the class, you'll be training like a model called ResNet 34. So that network has 34 layers. And for every layer, it will have a weight matrix. And the dimension of the weight matrix is a function of the input dimension and the output dimension. So this W1 has 2 inputs and it has 3 outputs, which I believe means its dimension will be 2 by 3. It might be 3 by 2. It might be transposed. Let me look real quick. Let's see. So it's input by hidden. Yeah, okay, cool. So yeah, so this will be a 2 by 3. And just throw it in the chat window. What will be the dimension of this weight matrix, right? Remember, it's the number of input units by the number of output units. So yeah, if you know, what will be the dimension of the W2 matrix? Yeah, 3 by 1. Great. Good job, guys. All right, great. Okay. So that's just a quick little overview of our neural network. Hopefully that all makes sense. Those are some of our key variables. And just a couple other things real quick. There's a few other variables that we keep track of. So after we get our output, right? So we basically take our input, we multiply our inputs by our weights, and that gives us an output. This output we usually call Z. So Z is it's called our activation. And then we take our activation, Z, and we pass it through our sigmoid activation function. And that becomes what we call an activity, A. So this is the output of our activation function is A. And this A gets passed through our next layer by matrix multiplication, which we'll get into in more detail in a minute. And that becomes another activation that goes through another activation function, and that becomes our output. So our output we're calling y hat here. So we'll get into that into more detail, but that's just a little summary of some of the key variables. So these are our forward equations, like I just mentioned. Can I make those bigger easily? Not that easily. All right. Okay, yeah, so Sai is asking a great question. He's saying, hey, is this a dot product or multiplication? Great question, Sai. So let me think. I could just answer, but I kind of want to, yeah, let me turn it back to the class. So Sai has asked a great question. He's saying, okay, as we move, what we're talking about is forward propagation. So we take our data and we move it through our network to make a prediction, right? And he's asking, when we have this, this weight matrix here and this input matrix X here, do we do a dot product? Or do we do a matrix multiplication? So Sai, that's a fantastic question. Let me try to answer it with another question, right? So if this were a dot product, right, what would be the dimension of the output? What is the dimension of the output of a dot product? Always 1, right? And how many numbers do we actually need out of this first layer? How many numbers do we need? Not 1, because you have to have an activation for each neuron. You actually need 3. You need 3 outputs. So for that reason, it's actually matrix multiplication. Yeah, great question. So it's not a dot product here. Good question. Cool. We will do what's basically a dot product kind of inside the neuron, but here we're kind of expressing the math a little bit differently. So these are matrix products. Good question. To make that confusing, we're about to look at the code. And the NumPy notation for matrix multiplication is np dot dot, which is terrible. So it's going to say dot, but it's actually a matrix product. Okay, so here is my Python implementation of our neural network. So have a careful look at this. This is the beginning of the code that you will be editing as part of your programming challenge. So here it is. Let's have a look. So I've defined, this is a Python class, and I've defined a few different hyperparameters. Let me just, actually, let's talk about it for a second. So hyperparameter is a big word, right? It's probably a fancier word than it really needs to be. So does anyone know, why are we saying that these are called hyperparameters? Why can't these just be parameters, right? Why do we have to put this hyper word in front of them, right? If you know the answer, throw it in the chat window. Why are we calling these hyperparameters? So good guess. Kind of getting there. Why not parameters? Why can't we call them? So we're not going to learn these. We're not going to learn these. Yeah, so Rohan's getting close. He's saying network structure. So let me back up a little bit. So these 9 numbers, right? I didn't tell you this. It's kind of written here, but I didn't tell you. So these 9 numbers, right? The 9 weights. A lot of times you're going to hear people, myself included, not call these weights. They're instead going to call these parameters. So they're going to call those 9 weights. They're going to call those parameters. Because people call those parameters and those weights. So we haven't gotten into this into a lot of detail, but when the neural network learns, just like the perceptron algorithm, when it learns, it's going to change those weight values. Changing the weight values is how neural networks learn, right? And like I just said, weights are often called parameters. So the parameters are what actually do the learning, those weights, right? Now here, if you look at this carefully, right, these numbers, these describe actually like the input dimension, right? Why is this 2? It's 2 because we were looking at the number of hours of sleep and the number of hours of studying, right? So this is not going to change. This is not going to be learned. It's always going to be 2. So because it's a parameter, but it's not one of the learned parameters, we call it a hyperparameter. So that's all it means. Hopefully that makes sense. Hyperparameter is something that's fixed. You can't change it. And it has to do with the neural network structure or something about how it's trained in general. Okay. So this just describes that we have 2 input units, we have 1 output unit, and we have 3 hidden units, right? And we could change those, and you actually will be changing these in your programming challenge. Okay. Now, what am I doing here, right? Can someone tell me in words, what is happening here? What am I doing? What am I making? What's going on? Yeah, so Hernan, Abhijit, great. Good job, Jagadish. Yep, perfect. So we're initializing random weights. Okay. Think back with me to the perceptron algorithm. How did we initialize our weights for the perceptron algorithm? 0, right? So this is different, right? I'm making my weights random. Okay. It turns out that in general, you're going to learn better with random weights. There's no like theory of this, but it just turns out you learn better. And there's actually a bunch of papers on this. You can read this. The most popular paper is probably called the Glow-Rot initialization. We'll get into this in deep learning. There's a bunch of theories or ideas about how to best initialize your weights. Here, I am just using what is that rand in? What does that in stand for in NumPy? Doesn't stand for random. What is that in? Not number, good guess. It's a certain kind of random distribution. Thank you. Yep, it's a normal distribution. Good. So this is a Gaussian or normal distribution of random numbers. Cool. And the input or the dimension of this matrix that I'm making, it's going to be input layer size, which is 2, by hidden layer size, which is 3. So this is going to be a 2 by 3 random matrix. Okay. And I'm also making my W2 matrix, which is going to be a 3 by 1. This will be a 3 by 1 random matrix. If you look at my math here, I'm actually just implementing exactly those equations that I shared with you. So I know this says np dot dot, but really this is a matrix multiplication, matrix mult. You can also use the @ sign for matrix mult, which maybe is a little less ambiguous if you want. I don't usually use it. I don't know. It just feels weird for me to have an @ sign in my code. I don't know why, but I don't like it. That's just a personal preference though. So here we're using our sigmoid function. This is that activation function thing. And here I've defined it so we can use it. There it is. Here I'm doing my second matrix multiplication. Okay. Here I'm doing my last activation function. So that is, in a nutshell, that is part of a neural network. So that's the forward pass. That's how we compute a prediction based on an input. Okay, so let's try it out. I'm going to initialize it. I'm going to take my data. I'm going to pass it through my network. So this is the forward method that takes my data and passes it through my network. And I'm going to make some predictions. So right now, if I take my data, pass it through my network, I get these numbers out. I get these numbers out. Okay. And what I'd like to do is I'd like to make a little plot, right? So I got 3 numbers out. And actually, let me just say one more thing really fast. So the output numbers, we usually call those y hat. We call them y hat. This is an idea from statistics. So see this little hat over the y right there. Hopefully you can see that. Does anyone know why we call our output y hat? Why is that the variable we've chosen to represent our output? Approximate is very close. It's not a vector. So I know that the hat notation is used for vectors pretty frequently in physics. The hat notation does not mean vector in this class. Great question. It's not a ceiling. Good question. Yeah. So Robert, I think Robert has said it best so far. Good job. So he's saying it's an estimate of y, right? So and remember, what is y? Y is our actual like ground truth like data, right? So y is this stuff, right? It's the actual data. It's this, right? So what we're trying to say is that the output of our network, it's an estimate of y, but it's not y, right? So we use the math y hat. That's very common in machine learning. So just a little, that's why we're calling this y hat, because it's an estimate of y, but it's not the same thing as y, right? And here, you know, I've passed my data through my network and I've gotten some y hat values. There they are. There's 3 of them. It's the same dimension as y, right? There's three inputs, 3 outputs. And here's a little plot, right? So this plot, it's a little bit small up here. Can I change that on the fly, I wonder? Let's see. What do I need? Just a bigger font size for my legend? Let's try it. Let's see. Font size equals 16. Oh yeah, much better. Cool. So blue is y hat. It's the estimate of y from our neural network. Green is the actual data. These are your test scores on those 3 tests, right? So looking at this plot, how are we doing? Throw it in the chat window. How do you feel about our neural network? Is it accurately learning the data? Yeah, so Pooja says bad, Akshay says bad, or me, I got a lot of bads. No one's impressed. All right, cool. So yeah, why does our neural network suck? Any ideas? Why is it not so great? Not learning. Yeah, so Akshay nailed it, right? We haven't trained it yet. This is just the beginning. It's learned nothing. It's just like a brand new newborn neural network. It's learned nothing yet, right? Okay, cool. Just random weights, hasn't learned a thing. All right, cool. Wonderful. All right, so to end this lecture, we'll hop to some announcements in a second. So you answered that question perfectly. So I just want to hit, I think, 2 more points, and then we'll do a quick announcement. Actually, I guess I kind of have a lot I want to say, but that's okay. We'll get into that next lecture. Here's what I really want to get into. So we have some bad predictions, right? They're not great. And maybe I'm going to stop at 43, and then we'll have 2 minutes for announcements. I'll stop at 43, 4 minutes. Okay. So before we can make our performance better, we need a way of measuring how bad it is. We need to measure how bad it is. Measuring how good or bad your performance is usually captured in machine learning by this idea called a loss function or a cost function. And the cost function that we'll use for this module, we'll use different ones later, but for now we're going to use what's called the mean square error. And this is the equation for the mean square error. Here it is right here. Okay, let's get into it a little bit, and let me make it just a smidge bigger so you can see it nicely. So this equation says, okay, take all of your y values, your actual ground truth data, subtract your estimates, square them, multiply by 1/2, and add it all together. So that's what it says to do. So let's check it out. We'll talk about why maybe it's a good idea in a little bit, but let's go ahead and code it up. So here I've written it in Python. So 0.5 times the sum of y minus y hat squared. There it is. There's our loss function. Okay. So now here's where life gets maybe kind of simple, maybe kind of complicated. So hopefully this feels simple. Excuse me. Hopefully this feels simple. So we only have one job for the rest of this module. So we have one lecture left, and the whole lecture we're only going to try to do one thing. All we're going to try to do is we're going to try to find some math and some code, math first, then code, that makes J, our loss function, as small as possible. And I didn't talk about it too much, but the smaller this thing is, the better. Because if you look carefully, right, what is this doing? So it's saying, let's take the current value, subtract the estimate, and square it, basically. So the closer y is to y hat, the smaller this function will be, and the better our neural network will be. So our whole job when training a neural network is to find the weights, find the combination of weights that make this loss function small. That's our whole job. That's it. So let's think about that for a second, right? So when I first learned about neural networks, I kind of thought this was going to be easy, and it's not that crazy, but it's kind of hard. It took till the 1980s to figure this out, really. So what I kind of thought in my head was something like this. This is kind of how I thought about neural networks when I first learned about them. So this is like that same kind of plot we saw, right? So we've got 3 pieces of data. We've got our y values. We've got our y hat values. If I change my weights, right, if I play with the value of my weights, just like I kind of am doing here in this animation, then the predictions will change, right? We'll get different predictions. And our whole job is to just find the 9 best values that make this work. And I kind of thought early on, why can't we just try them all, right? Which is kind of related to our last module, right? Why can't I just try all the weight values until I find one that works? It turns out you really can't do that. And the problem, and I guess, yeah, sure. So the problem really is something called the curse of dimensionality. And it just comes down to the fact that there's just going to be too many values to try. This is just for 9 weights, right? So modern neural networks will have on the order of tens of millions of weights. So you just can't try them all, right? It's an NP hard problem or NP complete, something like that. It would take way too long to try them all, so we need a different approach. The approach that we're going to use, and this is part of backpropagation, well, actually we're using backpropagation, and then on top of it we're doing this. We're going to do this thing called gradient descent. And gradient descent is just, it's super cool. The fact that it works is just, it's so interesting. So this is where we're going to pick up next time on gradient descent. Please do go watch the videos. Please do a little bit of math. Last year we did a kind of an interactive thing. I see Arvind and Rohan are chatting about last year. We did an interactive thing where we kind of worked this out on paper. Maybe we could do something similar on Tuesday. We'll talk about it. But there is some advantage to kind of working through this math yourself, because basically in the next lecture we're going to try to estimate what are called the gradients. These are going to tell us how to change our weights. It's going to tell us how to update our weights to learn, basically, and we're going to do some math to figure that out. So we'll figure out how we want to handle Tuesday. We'll let you know. But great, so let me go ahead with only 1 minute left yet. I apologize, guys. Let me turn it over for a quick announcement from Aravind about booking through Calendly. Hey, Aravind, are you there?
Yeah, yes, Professor.
All right, great, go ahead.
Could you see my screen?
Yep, we got it.
Okay, so all the project meetings we have are conducted through either the meeting rooms of mine or Rohan. So this is the schedule. So every group will have a meeting on alternate weeks. So the group 1, 2, 3 have meetings this week. So they'll again have it on 27th, 29th or 30th. So we request the groups to book your slots only for this, but only through the particular week. So this is the place where you can actually book your slots. One thing we wanted to make sure, because to book slots only on your particular week is, we don't want to reschedule every time, because there might be chances that uh, rescheduling might be necessary, and we want to give equal opportunity to all the teams. Like there are 8 slots for 1 week. On Tuesdays 2, on Thursdays we have 2, and on Fridays we have 4. That makes total of 8. So just go to the spreadsheet, check which week you have a meeting, and click on the calendar link, and you can just book your slot. All the links are available on course page here. This is the schedule. This is the Calendly link, and these are the meeting rooms of the TAs. And few people have asked me like the Calendly is in my account, but their corresponding TA is Rohan. That should not matter. Like we'll discuss internally. So you can just join your corresponding TA's meeting room, and we'll be there for the meeting. That's it. Thank you.
Great, thank you so much, Arvind. All right, we are a minute over, so we'll go ahead and wrap up. Thank you for your time today, guys. I hope you enjoyed lecture. We'll have one more lecture next week on neural networks. Do go watch the videos, have a look at the mathematics especially. And then next week from today, we'll have another, should be a really good guest lecture. So thanks, guys. We will see you next week.